This is Dr. Wood with Citadel Civil Engineering. This is CIVL203 Dynamics, Learning Objective 5.1, looking at rigid body equations of motion. Just as a reminder, this is in chapter 16 now of Baron Johnson's Dynamics textbook, where we're looking at these things. And the question has come up, where are we going to use dynamics? Well, this is the tool that really will let people use dynamics. So for example, if I have my mechanical engineering students who wanted to be able to design a bicycle frame, this is the tool that's going to do it. We've got all sorts of forces where we have things that are moving, but then we're also looking for their internal forces. So if we think of dynamics as the natural follow-up to statics, rigid body analysis, then we can actually use everything you've been learning in mechanics of materials and apply it to dynamics as well. So you can actually take bodies, cut them open, expose the internal forces just like we did in statics, and then relate those internal forces to the stresses and strains on the body. So you could do that for something like a bicycle. You could look at it for the Baja team. Here's our Citadel Baja team if you want to be involved in that. And then for my civil engineers, it's a moving bridge. This is the bridge that goes out to Sullivan's Island here in Charleston, and it's a swing bridge, so it rotates. And so we can think about doing fixed axis rotation about the center column as it goes forward, and we have a truss, so it's moving. And so there will be a need to be able to analyze that body, not only when it's acting as a bridge, a static system, but also when it's acting as a dynamic system as the bridge is rotating. Additionally, aspects like impact, wind loads, earthquake loads, all of those use dynamics potentially when we're looking at structural dynamics. Much of the dynamics, the way we're learning it, gets hidden down in code, but the general principles are there. And so developing those mental models to allow you to do that's very important. So with that kind of background in place, I'll leave that bridge a little bit to leave you inspired. I want to put some theory on the board of how our rigid body kinetics is going to go. And so if we recall the definition of kinetics, rigid body kinetics looks at the relationship between force, mass, and our kinematic properties, and our equations of motion, which is what we're going to talk about today, is based on Newton's second law. And so we said that in the case of translation, our translation component is going to be exactly what we did for particle. So we're going to say that the sum of the forces as a vector is going to be equal to the mass times the acceleration. Now the trick to making this true in the general case for a rigid body is that this equation is going to be applied at the center of gravity. Okay, so we're going to find the center of gravity for the object, and we're going to figure out what the acceleration at the center of gravity is, and then mass times acceleration of the center of gravity is equal to the sum of the forces. So that's what we're doing for translation. This is the same as our particle work, our particle kinetics going forward. It's still true. Now, when we think about the rotation component, the way that Newton, so we'll remember that when Newton wrote his second law, he actually wrote it as the sum of the forces is equal to the change in linear momentum with respect to time, and that this is true when mass is a constant. He also wrote the rotation component as, if we had sum of the forces, what went with it in, think about what went with it in statics. Sum of the forces equal to 0. We also said sum of the moments is equal to 0. Well, now in rotation, we're going to say that the sum of the moments about the center of gravity is equal to the change in angular velocity with respect to time, like so. So this is going to be the first derivative of angular velocity, angular momentum with respect to time. So sum of the moments is equal to the first derivative of angular momentum with respect to time. This too is at the center of gravity. And so we're summing our moments about the center of gravity. Now, this is a little different from how we did it in statics. In statics, we said we could pick any spot we wanted to sum our moments. But in dynamics, we're going to need to sum our moments about the center of gravity going forward. And in your textbook, this is in section 16.1b, where you see the derivation of this blown out for you. Now, the cool thing about this is because both of these things are happening at the center of gravity, what we're talking about is equivalent systems. So we spent a fair amount of time in statics figuring out how to calculate the force, resultant force, and resultant moment at a location. And that's what we're looking at here. We're going to look at the external loads and reactions, wherever they might be, and that's going to give us our resultant force and resultant moment, but we're going to calculate those at the center of gravity. That's going to be our big thing there, at the center of gravity. So naturally, we're all excited to calculate the first derivative of angular momentum with respect to time, but it turns out, as promised, we're only going to be working on this in plane or 2D rigid body kinetics. And so these two equations are the general forms of the equations. They're true in 3D, absolutely. But in 2D, this simplifies a fair amount for us. We're going to say that the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. And we're going to say that the sum of the forces in the y direction is equal mass times acceleration in the y direction. And this was just like what we did for particle kinematics. So there's nothing really new to see here. It's exactly what we did before. The new piece, and this is really the only new piece in this whole deal, is that we're going to say the sum of the moments about the center of gravity is going to be equal to the mass moment of inertia, I, about the center of gravity, times the angular acceleration, alpha. So sum of the moments equal to I alpha. And so this is in your FE reference handbook on page 82. So you can check that out there. The trick to all of this is that this has to be at the center of gravity. Have I said that enough times yet? We're doing this at the center of gravity. Now, you can do it at a different location, different from the center of gravity, but then you have to introduce a parallel axis theorem to this equation. It's in your FE reference handbook. It's in your textbook. You're welcome to do that if you can make it work. But I think it's simpler most of the time, or at least in this class, to just calculate our sum of the moments about the center of gravity. Now, in order for us to be able to do this, we have to be able to calculate this mass moment of inertia. Mass moment of inertia. And we talked about this in statics. And we said that the mass moment of inertia, I, about the center of gravity, was going to be equal to the integral r squared dm. So everyone's super excited about doing integration. Or we can talk about Rm squared times m, where Rm is going to be our radius of gyration. So we have a radius of gyration. Your textbook actually uses the symbol K for radius of gyration. The FE reference handbook uses the symbol R sub m for the radius of gyration on page, I believe it's on page 82 as well. And it's going to be equal to the square root of I, about the center of gravity, divided by the total mass. So the idea of a radius of gyration is saying it's a measure of kind of the center of mass away from the axis. And so I've actually got a shape that we analyzed in statics that we can talk about. So there's, y'all remember this guy? This little part piece. We calculated some moments of inertia for it. We calculated the centroid location. Right now we're going to talk about the moments of inertia. So we said that we could have an axis about the centroid and the x-axis, and it would spin, right? Well, the radius of gyration is measuring kind of the center of mass, how far away the mass is from that axis. We could do the same thing on the y-axis, and here we'll notice that it spins easier because our eye is smaller. Our radius of gyration, all the mass is closer to the center, right? And so that radius of gyration is lower, meaning that our I value is going to be lower, which means that for the same moment, we're going to get more angular acceleration. And so that's what you see there. We also, since I've got it here, we managed to calculate the major principal axis. This is the biggest moment of inertia. And the minor, so the smallest moment of inertia, smallest rate of gyration. You see how all the mass has moved toward that axis? And so it spins a lot faster because my radius of gyration is smaller, which means my mass moment of inertia is smaller. And since I'm applying roughly the same moment when I slap it like that, my alpha is a lot higher. So that's kind of what we're looking at there. Now, it'll also slow down faster because I'm getting the same sort of resistance against the handle of my screwdriver there. And because that resistance is generating a moment, right, about the same moment, my eye is smaller, it'll also decelerate faster. So both directions work there. So hopefully that's helpful to you as we think about the mass moment of inertia and the radius of gyration. You can find all of this in your FE reference handbook on page 84. And in this class, I'm going to stick to probably either telling you the mass moment of inertia or telling you the radius of gyration in the mass, so that you just do the radius of gyration squared times the mass, and you're basically in business. Again, this is in your book, more things you can think about. Point out that we've got 3 equations we can solve for up to 3 unknowns. Very frequently, those 3 unknowns are going to be our accelerations. Or we might have some sort of acceleration requirement, and we're calculating the forces or moments required to achieve that acceleration. So those are kind of the way that typically will work. The last thing I want to point out is that in the diagrams that are going to go with these, we're going to draw free body diagrams. And y'all know how to do free body diagrams in general, so I won't spend a lot of time on that. But we're also going to do our kinetic diagrams. And the big thing about the kinetic diagrams is that we're going to put our inertial terms, so mass times acceleration and I alpha, at the center of gravity. So if we have some object, we're going to have the center of gravity here, right? And when we do our inertial terms, we'll have MAX, MAY, and I alpha as our inertial terms on our kinetic diagram. And on our free body diagram, we might have all sorts of different things happening. Forces, maybe some moments applied in different locations, right? So we'll have our free body diagram, but our kinetic diagram is always going to have those inertial terms at the center of gravity. And then when we calculate our sum of the moments here, we're going to calculate it about the center of gravity. So those are our 2 big takeaways. Everything's going about the center of gravity. We've got our 3 equations. Big ones, sum of the moments equal to I alpha. We now know about mass moment of inertia. We've talked about it before. Our main usage is going to be R squared M. And we know that we can draw our free body diagram and our kinetic diagram in order to solve for these things. The big things being that in this class, at least, we're always going to use this equation by doing our sum of the moments and our inertial terms on the kinetic diagram at the center of gravity. We'll spend some time working on example problems, and so I look forward to doing that with you on the Zoom meeting. Take care.